You only have one gap, bitch.
Make sure that there are 3 stages. Is there enough staple ones over there? Maybe. Perhaps.
It should be 3? Oh yeah, I think it's 3. Just counting 4.
So we're gonna continue with the gases through a pipe. And yes.
Quick question. So, when we're doing these CPPM calculations, and let's say like that corner thing is like the container of gas, when you're saying the CPPM is like 10, is that like in the immediate area of the pipe, or is like that once it reaches steady state, like that's the room?
So that's a good. Did everyone hear that? Right. So this 10 ppm that we were just, if this is the hydrogen sulfide cylinder tank, where's the CPPM? So the calculation, if you remember, was actually based on a room. But that's why we have the mixing factor. So it wouldn't really be right here at the tank. It's assuming that you have some kind of room with a certain ventilation rate, right? And that's what it's based on. But as you know, obviously, we're not going to have a homogeneous mixture in here, which is why we're using the ventilation coefficients. So if we had perfect mixing, the K would be 1. But that's not really a realistic. Right. So if K would be 1, that would probably be more like here.
Okay.
Right next to it. While what we're calculating with the 1/8 that we had would be more like the room.
Okay. Cool.
Based on the ventilation rate that we had. Any other questions? So what I did on the handout, obviously, I'll put a couple of slides first for we went through more, but just here's the difference between the hole in the tank and what we're going to look at as well, which is flow of gas through a pipe. Okay, so we're going to, now we have 4 different conditions to look at. We can have adiabatic flow. Okay, that means if we have a gas expanding in a pipe, adiabatic, there's no heat transfer from transfer into or out of your pipe. It's adiabatic. The other is isothermal flow. Okay, if you have adiabatic expansion, right, you go from one pressure to another. You have P1, T1 up here, and then P2 down there. Your T2 will be unknown. Right? That was part of the problems we had in thermo. Had to calculate what the temperature is on that end. Right? That's where we introduce the entropy balance. Okay, we're not going to do that here. Okay, we're going to look at these 2 cases, adiabatic and isothermal. Right? And then we have, again though, we have non-choke and choke flow. Okay? So let's look at, obviously what we're looking at again is solving that mechanical energy balance. But we're actually not going to look at the conditions, we're just going to look at what does the end result look like. Okay, so we're now looking at adiabatic non-choke. Okay, we start up here, P1, T1. We're now looking at a pipe, not a tank. Okay, and we have a U1 here. If this pressure, if P1 is higher than P2, then U2 is going to be higher than U1. Okay, we now have a compressible fluid. Okay, so our U1 is not equal to U2. Right? For this particular case, U2 is below the sonic velocity, so we have not reached choke conditions. In other words, our P2 down here is larger than our P choke value. Okay, now the authors have introduced the Mach number. Okay, so who knows what the Mach number is? I'm sure you've had. All right, and then obviously we've already talked about the T2 is unknown. So what's the Mach number? That's right. That's right. So is the velocity that you have speed to the speed of sound, right? See these, right? These jet pilots talking about being at Mach 4, right? That means they're going 4 times the speed of sound. They have broken through the sound barrier. Now we can't do that. Okay, so our Mach 1 is our maximum, right? So under sonic conditions, our Mach 2 at the other end will be 1. Okay, so for an ideal gas, the speed of sound here, which they call A, can be calculated from this, which is right depending on the conditions and the heat capacity ratio of that gas. If you calculate it for air at 20 degrees C, it's about 344 meters per second. Okay, I'm sure you've heard that. Okay, so how does that come into here? So why is this introduced? Well, it's not really, I prefer that you use this equation. So if you have adiabatic non-choke flow, this equation is more intuitive to me. It's complex, as you can see. But if you look at it, right, it's, what do we have? We have the heat capacity ratio. We have P1 and P2, T1 and T2, right? That's all we have. Now, it's not like we can solve this easily for T2, which is what we need to do. And then we have a pipe term. So this is what we've seen. You've seen this before, 4FL over D. So that's the fanning friction factor. Okay. So for non-choke flow conditions, what we have to deal with is we solve this equation here for T2. Okay. This is why I'm not giving you a quiz on this one. Okay. We're doing a homework so that you can actually solve it. Okay, and then once you have T2, you can go into the equation for mass flux. So for some reason they decided to introduce G as the mass flux. So right, kilograms per square meter. Okay, instead of having just QM equals A times this. Okay,
Shouldn't there be a time there if it's flux?
Yes. Yes. Thank you. There's a second. It's kilogram per square meter and second. Okay, I'll try to fix that. Can you fix that in your notes? Very observant. Clearly, these are the same things I had last year. Except what?
Nobody got it.
So, okay, so this is the most straightforward way I feel to solve this. There is an alternative equation in the book where they use Mach numbers. Okay? The reason I'm putting this up here is because we're going to look at the same equation but for choke flow. Because for choke flow, it turns out that using the Mach numbers is actually easier. Okay? So for non-choke flow, so this is basically the same equation as the one before. It might look simpler, but to solve it, you have to calculate Mach 1. Right? Then you solve it for Mach 2 so that you can calculate the mass flux in that case. Okay, so I don't know, I just prefer this one. It's easier to deal with, in my opinion. Okay, so that was adiabatic non-choke flow. So we're still looking at adiabatic, so there's no heat transfer between the gas and the surroundings. But now the surrounding pressure is below P choke. Okay, so the gases are come out of this pipe under choke conditions, right? We're at the sonic velocity, or our Mach here over is equal to 1. Okay? We still don't know T2 though. Right? So if we look at the same equation, so now they don't even bother putting it up in terms of T1 and T2. but this one is a little simpler, in my opinion. So for choke flow, you have your Mach 2 is equal to 1. Just, you could put in the other equation, right? You solve this equation then for Mach 1, where they've introduced the capital Y here. That's just a function of the Mach number and the heat capacity ratio. You solve this for Mach 1, and then you put it in and you calculate G choke.
What's the speed of sound?
Speed of sound is dependent on your conditions, right? So it's 344 meters per second in air at 20 degrees Celsius for an ideal gas. Okay, so that was our first, that was adiabatic. So how does it change if we have isothermal flow? Okay, so now we have T1 is equal to T2, T2 is equal to T1. We take the first non-choke conditions. It looks a little simpler, and obviously it's simpler because T1 is equal to T2. So this is the easiest one to solve, in my opinion. You solve this one for G. Now you have a mass flux straight in here. This one to me is easier to solve than this one, right? You solve this one, then you have to put this, your calculated Mach 2 into your equation for flux. Here you can solve for flux immediately. Right? And that one you can actually solve. Right? So I would use that one. If you have choke flow conditions, so for some reason under isothermal conditions, your Mach choke is actually not equal to 1. It's equal to 1 over the square root of the heat capacity ratio. Okay, so simplifies things a little bit. You can still not directly solve for Mach, or at Mach 1 here that you need to calculate your G choke. And again, your G choke, your QM then is equal to G times the area. If we go back, so now your slides are you don't have this on there, but if we look at the procedure for each one, right, here's what I would recommend you doing. So for each one, you have this term, your 4FL over D. So you calculate the fanning friction factor, and for the condition that we're looking at, gases now, right, fully developed turbulent flow is typically a reasonable assumption. Right? That means you can solve for your fanning friction factor directly as long as you have your smooth, right, the smoothness factor, the roughness factor of your pipe and the pipe diameter. Once you have that, you can plug that into this equation, adiabatic non-choke. You solve this one for T2, and then you calculate QM for, which is A times your G, with the numbers that you got. So once you have T2 from here, all your numbers in here are known. And that's how you get your QM. That's a QM that you can put directly into your ventilation calculation, for example. Right? So that would be for non-choke flow. Choke flow, it's the same procedure. You calculate the fanning friction factor, but you use this equation to calculate Mach at conditions 1. And then you calculate QM, area times your G choke, which is equal to this, which now you have T1, P1, and you calculated your Mach 1. Same thing, right? You need the fanning friction factor for each one. That's your first step. You can plug that into your equation. You calculate G from this one, and then QM. Okay, so as you saw, you don't have to use, there are some alternative equations. What in these last few slides is my recommended approaches, right, to solve these. And then isothermal choke flow. Calculate the fanning friction factor, your Mach 1 from this equation, you've got your F there, and then your QM. Okay, so, right, your step 1 and 3 are almost step Step 1 is the same for every single one, right? Step 3 are separate for choked and non-choked, right? And then these are, you have to look at whether it's isothermal conditions or adiabatic. Okay. Now, if we look at all these 4 cases, there's one case in particular that's most common than any other one. The first, of course, as we saw from flow through a tank, is that it doesn't take much for you to have choke flow, right? In other words, if you don't know, you assume choke flow, do the calculations, and then you go back and double check that your choke flow is correct, right? That you did that was the right assumption. But if we look at the choke flow in both cases, right, are the most typical. It's actually difficult for us. You'd have to have a very low pressure on the other end to have non-choke conditions. So, right, and if you look at the difference between adiabatic and isothermal, so since we already know that choke flow is the most common, it is very difficult to have an isothermal case under choke flow conditions. You have to have an extremely efficient mass transfer, which is probably not existent, right? Because it's coming out of there at the speed of sound. You can imagine what kind of heat transfer rate you would need to make that flow isothermal, right? So the most typical conditions that you will use is adiabatic choke flow, okay? So in other words, where do we have adiabatic choke flow. So if there's one equation that's right, that's more important than anyone else in this part, it would be this one. Okay? So well, you actually have to use the Mach numbers. Okay. Any questions so far? We're not going to derive these equations. In fact, they're not derivative. They're not derived in the book, and I'm not going to attempt that either. So we're just going to use them. So let me see where we are. So 413, that's a cylinder in the laboratory, contains nitrogen that's 2200 psi, absolute. If the cylinder falls off and the valve is sheared off, estimate the initial mass flow rate of nitrogen from the tank. If there's a hole of diameter 0.5. I'm going to leave you to attempt this one because this is clearly just the flow of gas through a tank. And in fact, you're just asking for your QM. So this is, you just plug everything into QM choked, right? And you can be certain that the flow is choked. It's 2200 psi absolute versus 14.7, right? There's no way it's not choked coming out of there. And the only thing you need is nitrogen with a heat capacity ratio of 1.41. So let's spend some time on 414 instead, which is same thing. We have a laboratory apparatus using nitrogen at it's 250 psi gauge now. It's a little bit lower, order of magnitude lower. It's still pretty certain that we have choke flow, but it's supplied from a cylinder through the regulator and then 15 feet of tubing. Okay, so we have 15 feet of 1/4 inch diameter, internal diameter, drawn copper tubing. So this tubing separates from the apparatus. We are asked to estimate the flow of nitrogen from the tubing, and we're told that the nitrogen in the tank is at 75 degrees Fahrenheit. Okay, so what did I say? What should we assume? What do you think? Choked? Choked? And if it's choked, it's probably adiabatic. In other words, this is what we need to deal with.